So basically, well, if we look at a grid, right, so first thing that you need to realize that a grid is a graph, right? So here is our graph, right? So I can take my point on a grid and I can move it around. What we'll need to assume, just for simplicity of analysis, is what is called periodic boundary conditions. So when I reach the end of my grid, I go back to the beginning, right? So this is called a ring graph, and these are called periodic boundary conditions. And basically, I can think of this as a cyclic group, right? So the grid with periodic boundary conditions is called cyclic group. It's denoted by Zn. And basically, 1D translations with periodic boundary conditions, it's exactly corresponds to this cyclic group, right? So mathematically, we can describe it as a modulo n arithmetics. So basically, I can shift my point, right, where I do everything modulo n, and modulo n tells me when I reach the end, I go back to the beginning, right? So n modulo n is 1, right? Or sorry, 0. And these are the elements of this group, right? And you can also see that here we have a very special case. So the special case here is that the domain itself is equivalent to the group on which acts on it, right? So I can identify every element of the shift group with a point on the domain, right? So I can say that I shift to this particular location, right? So this is exception rather than a rule. If I have time, I will show at the end how we can define a general convolution. So in general, you can define convolution on a group, right? So it doesn't even look like a convolution if you make it most general. But again, here we have this special case where basically there is a one-to-one correspondence between the structure of the group and the structure of the domain. So again, in general, this is not the case. So this is just one-dimensional case, so it will be convenient to analyze everything in one dimension. But of course, you can also think of two-dimensional grids, right? So what is a two-dimensional grid? It's just a tensor product of two one-dimensional grids, right? So we denote it by this cross, right, or the Kronecker product, right? So it's product of Zn's. And of course, you need to account for the boundary conditions, right? So I wrap around in each dimension, and topologically, this has a structure of a torus, right? So this is how this grid with periodic boundary conditions in two dimensions look like, right? So wrapping around here along this dimension and along this dimension, okay? And of course, we can go to any dimension, right? So I can take a d-dimensional Kronecker product, and I will get a d-dimensional grid, okay? So same as we had with our geometric deep learning blueprint, so we now need to define the space of signals on our grid, and again, it will be convenient to think of scalar signals, so we can identify them with Rn, right? So scalar valued signal at every point of the grid, right? So together it's Rn, and I can represent them as n-dimensional vectors, right? Where I index them from 0 to n minus 1, right? Why I want to use between 0 to n minus 1? Because it's convenient with modulo n arithmetics, right? So when everything wraps around with periodic boundary conditions, okay? And I remind you, so we talked it, so you heard it yesterday in the discussion about group representations. So again, we have a group that acts on a domain, right? So we have something that moves points around on a grid, right? So translations. We lift it to the space of basically linear transformations between signals that live on these domains, right? So the group representation acts between images or between vectors, right? Signals that live on the grid, and this is a matrix, right? So how does a shift operator look like, right? So the representation of the translation group looks exactly like this, right? Very simple. So our domain in this case, it's a grid. Basically, it's a grid, right? And the shift operator looks like this. So if you look at it from a different perspective, this also, you can think of the shift operator as the adjacency matrix of the ring graph, right? It's a directed graph. So this is actually will allow us, so this is one of the ways of extending convolutions to graphs. So you can think of the shift operator, right, as the adjacency matrix of the graph, okay? So, but again, we'll talk about it later. Okay, so this is the shift operator, right? So a matrix that has these off diagonal elements. right? And what it does, it's a left shift, right? So I shift to the left. So if I have this vector x0 through x5, let's say, I multiply it by the shift matrix, I get the same vector where everything is shifted with periodic boundary condition, right? So I can get a vector x1 through x5 and then x0, right? And for every element of the group, I can basically just take the power of the shift operator, right, for some k. The inverse element is the matrix transpose, right? So if I transpose the shift operator, I will get the shift in the opposite direction, right? So this is the right shift, right? So that's the inverse element. And also, you can easily see that S is an orthogonal matrix, right? So S transpose S equals S transpose, right? So shift left followed by shift right is identity, or shift right followed by shift left is also identity, okay? So what do we know about orthogonal matrices? They have orthogonal eigenvectors, right? So we'll see that it is helpful, right? So this is how we get the Fourier transform. Okay, you can also prove that it's commutative. So this is an abelian group, but I leave it as an exercise. Okay. So how do we do two-dimensional shifts, right? So if you have an image, and in most cases, right, so when we talk about convolutional neural networks, usually we apply them to images. Again, we can represent them as n by m dimensional matrices, right? So this is the image of n by m pixels. So I can shift it from the left, right? So it applies column-wise, and I can also shift it from the right, and this applies row-wise and column-wise, right? So I can shift both ways, right, by multiplying my image from the left and from the right. Alternatively, I can take the image and stack it column-wise into a long vector, right? And then I can do the same thing by Kronecker product, right? So I can multiply it by a bigger matrix of size nm by nm, right? And this is basically a kind of a block matrix that looks like this, right? So this is called the Kronecker product, okay? So it's exactly the same thing, it's just represented in a different way. So if you like to have your operations as matrix multiplying a vector, so that's a way to do it, okay? Now, again, we have functions of signals on grids, right? So this is basically this will be our neural networks, right? So it's a function that takes a vector and produces a number, for example, right? Or a label or whatever you want, right? And we've seen in the general discussion on the geometric deep learning blueprint that it is sufficient to consider local linear invariance and equivariance, right? So because we know that we can combine them together with element-wise nonlinearities, poolings, and so on. And this way we get, basically we can construct nonlinear functions, right? So linear invariance will look like this. So it's a function that takes a vector and produces a scalar. And linear equivariant is a function that takes a vector and produces a vector of the same dimension, okay? So let's start with the first one, with the invariant, right? So an invariant is very simple. I need a function, right? So if it's linear, I can always write it as an inner product, right? So you can actually prove it very easily, right? But basically, I can pick up a vector v, right, and n-dimensional vector, and take its inner product with my input x, okay? Now, to be invariant, it has to satisfy that for every shift, right? So for every element of my translation group, I produce the same output, right? So basically, the output is unaffected by the shift. Okay. When will this be possible? So how should V look like in order for this to happen? So the only option is a unit vector, right, or a constant vector, right? So it doesn't matter how it's normalized, but basically a vector of ones, right? If and only if, right? And you can prove it, but this is a special case of a general case, right? So if you want to be linear G invariant, right, with respect to an action of the group G, then the only function that is possible that is linear is a function of the group average, right? So I need to take the average of my input along the elements of the group, right? And in case of translations, this will be just the average color of my image, right? So it's not very expressive, right? So it's, if you give me an image, I will tell you that you need to base your predictions only on the average color of the image, right? So it can be anything, more or less. So it's not very descriptive, right? So that's why linear invariants are not very interesting. And we're interested in linear equivariance, right? And then we can combine them with nonlinearities as we typically do, right? In convolutional neural networks, we interleave our equivariant layers with nonlinearities, with nonlinear activations, with pooling, and so on. Okay. So what is a linear equivariant? So translation equivariant. So it's a function of this form, right? So linear function. So it looks like Cx, right? So C is some matrix, size n by n. And now we need to satisfy commutativity with the shift, right? So any shift, so means that I can first shift by k positions and then apply the matrix C, or the other way around, the result will be the same, okay? So basically Cx is translation equivariant if and only if C commutes with the shift operator, right? So Cs equals Sc, okay? So the question is, how, of all possible matrices, which ones commute with the shift, right? So how do these matrices look like, okay? And this is exactly what we call the convolution. Okay, so let's derive it actually. How do we get the convolution? Okay, so I remind you, our condition is Sc equals to Cs, right? So first shift, then convolution, or the other way around, okay? So what is Sc? Let's write it explicitly, right? So here's the formula for the matrix multiplication. So the ijth element of Sc looks like this, right? So I need to take Sik multiplied by Ckj, right? And then sum over all k's, right? From 0 to n minus 1, okay? Now, what is S? That's S is our shift operator, I remind you, right? So this is how this matrix looks like. So it's a matrix of zeros, and in the first diagonal, right? Not the zeros diagonal, the first diagonal, it has ones, right? All the rest is 0, okay? So I can write it explicitly, right? So this is basically, I can write it as a delta function, right? So delta function that looks like this, right? So delta I minus k plus 1, right? So this function is 1 when the index here is 0 and 0 otherwise, right? So when I minus k equals to 1, right? Or I minus k plus 1 equals to 0, then we get a 1, right? So basically out of this sum, it leaves only a single element in each summation, right? And this element is Ci plus 1j, okay? Now I can do the same thing, so for the opposite multiplication, right? Cs ij looks exactly like this, right? So again, I plug in the definition of S, and I get Cij minus 1, okay? So just let's look at these elements, okay? So here is position I plus 1j, right? And here's position ij minus 1. And since we assume from commutativity that these two elements must be the same, right? And this is true for every I and j, basically we get that these two elements everywhere are the same, right? So we get a matrix that looks like this, right? So every case diagonal will be constant, okay? And again, I remind you of the boundary conditions. So when we reach the end of the matrix, we need to wrap around, right? So it's all modulo n, okay? So basically, it will be a matrix that looks like this. All diagonals are equal, right? So basically, it looks like this. So I can form it by taking a vector, right? So taking a column or a row, but in this case, it's a column of parameters, and I just append each column is shifted, again, modulo n with periodic boundary conditions by one position, and I form the columns like this by shifting them each time by one position, right? And this is called a circulant matrix or a convolution matrix. So this is how it looks like, okay? So when I multiply by this matrix, this is how the multiplication looks like, right? So it looks like theta I minus j modulo n, of course, xj, right? So this is exactly the definition of convolution. But again, it's not a formula that lands somewhere out of the blue. It's we got it from our consideration of translational symmetry, right? So the commutativity with the shift gave us this special structure, okay? So linear translation equivariants are convolutions. Now, convolution has a long history, and there is a debate who actually invented convolution. So some different sources attribute it to Laplace, but I think D'Alembert was the first to introduce it, and it actually was not called convolution initially, so it had multiple names, and convolution appeared, I think, in the 30s or 20s in the English literature as translation from German. So it's pretty relatively recent naming convention. Okay, so again, in our blueprint, right? So we have basically a domain which is agreed. We have the translation, right? So the cyclic group in this case, and its representation is the shift operator, and the equivariant, the linear equivariant operator, is the convolution. Okay? So basically, this is what we've seen so far. So linear translation equivariants are convolutions. Convolutions emerge from translational symmetry, and grids are special cases of graphs, but with more structure. Right? So again, if we compare these architectures, so we started our discussion with MLPs, right? So the most general, fully connected layers, right? So in this case, if you look at the weight matrix, it's arbitrary, right? So there is no symmetry here, right? So that you can think of a trivial symmetry group, right? So in this case, we have n squared degrees of freedom, right? So every input is connected to every output with a different weight, right? So it's n squared different parameters, right? This is one of the reasons why it's dimensionality course. You have a lot of things to learn, right? And if you input a gigantic image, then your parameter space is gigantic. So when we talked about learning on sets, right, in deep sets, when our group is permutation, right? So permutation is a very large group. So I can distinguish only between myself and not myself, right? In the graph, I can distinguish between myself, my neighbors, and everybody else, right? But it's similar situation, so it's order of one parameters, right? So it's either me or not me, okay? So here we have some kind of intermediate case, right? So in case of translation, right, or cyclic permutations, we have order of n degrees of freedom, right? So we have this circle structure, but still we distinguish between each element on the grid, okay? So this is how CNNs are structured. Okay, and again, if we make this analogy to the graph, right, because we said that the grid is a special case of a graph. So remember how we had the aggregation on the graph, right? So we had our cells, right? So the node I and everybody else, right? So all the neighbors, let's say nodes J, right? So we had a distinction between the feature the node I and the multiset of the neighbors of this node I, right? So same thing on the grid, but on the grid the difference now is that we have the order, right? I don't have these neighbors coming in arbitrary order. On a graph, I cannot order them canonically. On a grid, I can. I can say this neighbor comes before me, and this neighbor comes after me, right? So this function can be more specific. And if, in particular, we're interested in linear aggregation functions, right, when this phi is linear, so on a graph, again, my only distinction is between myself and not myself, right? So these are the different parameters. On a grid, I can distinguish between each and individual neighbors, right? And that's how the graph convolution looks like versus the traditional convolution on a grid, right? We can distinguish between different neighbors. Okay, is it clear? Any questions? Okay, so we also know that there is a relation between the Fourier transform and the convolution, right? So basically, this dual picture, you can do the convolution in the spatial domain, or you can do basically spectral filtering, right, in the Fourier domain. Okay, so how exactly do we arrive at this? I will now derive the Fourier transform again from first principles. Okay, so first a reminder from linear algebra, when two matrices commute, right? So in other words, AB equals BA. This happens if and only if they are jointly diagonalizable, right? So a reminder. Usually this is not the case, right? So typically matrix multiplication is not commutative. In other words, AB is not equal to BA. But if this happens if and only if the matrices are jointly diagonalizable. In other words, there exists a matrix of eigenvectors, let's call it phi, such that it diagonalizes both A and B. They might have different eigenvalues, but they have the same eigenvectors, right? So here I should say that I'm a little bit cheating in this discussion because the eigenvalues might have multiplicity, and therefore it's not completely correct to always talk about eigenvectors, so we need to talk about eigenspaces, but let's assume that there is no multiplicity, so we are talking about eigenvectors properly, right? So they have single multiplicity, okay? Now in our case, we have our convolutions, right? So these matrices with this special structure C, they commute with the shifts, right? So we can, because they all have the same eigenvectors, we can look at the shift operator by one position and compute its eigenvectors by hand, right? And these will be also the eigenvectors of all the convolutions, right? And we'll see surprisingly that this will actually be the discrete Fourier transform, okay? So now what I will try to do is to derive the eigenvectors of the shift operator. So because we already said that it's orthogonal, right? So it has orthogonal eigendecomposition. So in other words, its eigenvectors look like this. So it's phi lambda phi star, right? Why do I write star? So star is transposed with complex conjugate. This matrix is not real because S itself is a not symmetric matrix, right? So we expect the eigenvectors and eigenvalues to be complex, right? And but it will be orthogonal, okay? And again, commuting matrices will have the same eigenvectors but different eigenvalues, okay? So what we'll do now is we'll derive the eigenvalues and eigenvectors of S, okay? So we assume that we have some x, right? So and it's not all zeros, right? So there is at least one non-zero element of x, okay? Then for all indices I, right? So and again, I remind you, everything is modulo n. Sx equals to lambda x, right? So what I'm writing here is that x is an eigenvector of S with eigenvalue lambda, okay? So what is exactly S, right? So I can write it explicitly. So S is a shift operator, so I can write this relation as xi plus 1 equals lambda xi, okay? I can do it also for other powers of S, right? So S squared, right? So with corresponding to lambda squared. So xi plus 2 equals lambda squared xi, right? And I can do it all the way up to n, right? So xi plus n, again, everything is modulo n, so this is equal to xi, right? And I get xi equals lambda n xi, right? And again, because we assume that not all elements of x are 0, right? At least one element is non-zero, so I can divide by this xi. And what I get is that lambda power n equals 1, right? So it means that the eigenvalues of S are complex roots of unity, right? So that's how we define the roots of unity, right? So they're elements on the unit complex square, right? And they look like this, right? So e to the power 2 pi I k over n, right? For k going all the way from 0 to n minus 1, right? So these are the eigenvalues of the shift operator, okay? So now we know how the lambdas look like. Again, we can plug it in here and we can compute the eigenvectors, right? So here x was the eigenvector, so allow me just for convenience of notation denoted by phi, right? So the k's eigenvector of S will look like this, right? So phi k, and this is how it looks like. And there is typically a convention of to normalize the eigenvectors to have unit lengths, right? So they are orthonormal. So we need to divide by 1 over square root of n to make sure that the norm, right? So the length of this vector is equal to 1, okay? So bottom line, this is how this matrix looks like, right? So the columns of this matrix phi form an orthogonal basis, and this is what we call the Fourier basis. So the first one is a constant vector, right? So this is what in signal processing is called the DC. So it has historical naming convention. So DC stands for direct current, right? So this is constant vector. The first one will be one full period of a sinusoid, right, or a complex exponential. Then you have 2 periods and so on and so forth, right? So this is how these functions look like, right? And if I take a vector and multiply it by these bases, right, and again, because the elements are complex, I need to take also the conjugate, I get the discrete Fourier transform, or the DFT, okay? So the Fourier transform is named after Fourier. He was a French mathematician and politician. So most actually of his career he spent as a politician in Napoleon's government. And the construction of the Fourier transform, or more correctly the Fourier series, was in relation to differential equations. So he was using this device to solve the heat equation. So it appeared in his book on analytic theory of heat. So we'll talk about it as well, right? But basically, this was the reason for the construction of the Fourier transform, to solve differential equations. Now, geometrically, what is a Fourier transform? It's just a change of the basis, right? So if, again, use this low-dimensional Euclidean analogy, right? And now imagine that we have everything in high dimension or even continuous space of functions. Basically, I have a vector I can represent it by projecting it on some basis, right? An orthogonal basis, right? So the standard basis looks like this, right? So these are just the standard Euclidean axis, right? How do I get this vector, right? So I take projections of my vector x on each of these basis vectors, right? This is what I call coordinates, right? Coordinates always depend on the choice of the basis, okay? And then I multiply the coordinates by the basis vectors themselves, right? And I get back my vector, right? So this is how we represent vectors, right? So what is the Fourier transform? I just change the coordinates, right? And how do I change the coordinates? In a way that doesn't change the inner products and doesn't change the lengths, right? So in Fourier analysis, this is called the Parseval or the Plancherel theorem. So basically what it means is that the Fourier transform is an isometry. It's a distance-preserving transformation, right? Basically, again, change of coordinates. So that's how you need to think of it. Now, what's the relation between convolution and the Fourier transform? So we know that DFT diagonalizes the shift operator S, right? And because of commutativity of the shift operator with convolutions, all convolutions, right? So it means that a convolution can be written like this. So any circulant matrix or any convolution matrix looks like phi lambda phi star, right? Where lambda are some eigenvalues, okay? And now we can express the convolution in the Fourier basis like this, right? So if I want to multiply C by vector X, so I just plug in my definition, right? Here it is, right? So I plug in here the definition of C, phi lambda phi star. So some of the phi's cancel out, right? And what is written here, phi star X, is the Fourier transform of X, right? So let's call it X hat, right? So this thing cancels out. Basically what I get is that I multiply the Fourier transform of X by a diagonal matrix of eigenvalues, and then I take the inverse Fourier transform, right? So multiplying by phi is the inverse Fourier transform, right? Or inverse change of coordinates, okay? So convolution becomes element-wise product in the Fourier basis, right? So that's exactly what we mean when we say that DFT diagonalizes convolution, right? And because on the grid, these matrices phi and phi star have highly redundant structure, we can compute this multiplication without explicitly multiplying by a matrix. We can actually reuse many of these multiplications actually quite efficiently. It can reduce the complexity of matrix multiplication from n squared to n log n. And there are many ways of doing it. So this class of algorithms is called the fast Fourier transforms or the FFT. So here's one example, the famous Cooley and Tukey algorithm from the 60s, right? So this was the bread and butter and still is the bread and butter of signal processing, right? So this is how you do filtering, right? Everywhere, in your iPhone, in your everything, right? So what is still remaining to say is how do the eigenvalues of C look like, right? So if I give you a convolution, I know that I can represent it like this, right? Like phi lambda phi star, but what is lambda, right? So how do these eigenvalues look like, okay? So I remind you that this C, the convolution matrix, is constructed from circularly shifted column vectors theta, right? So let's express it like this. So I would like to express it C phi k equals lambda phi k, right? So these are its eigen vectors, and now we are interested in the lambda, right? So what these lambdas are, okay? So let's just write it explicitly. So this is how C multiplies phi, right? And phi is the kth column of the Fourier matrix, right? So basically the kth frequency of the Fourier transform, okay? So let's just take the first row multiplied by this vector, right? And we need it to be equal to lambda k. Okay, so here's lambda k, and this is the first row, theta 0, theta n minus 1 by e to I 2 pi k over n, and so on and so forth, right? Again, I remind you that everything here is modulo n. So this n, for example, right, I multiply by n and divide by n. So here I have a full period of a complex exponential, so I can ignore it, right? So I can just remove it. Basically, this n goes away. I get minus I 2 pi k over n, right? So here it is, right? I just rearrange things. And it's convenient for me then to take theta 1 in the beginning of the summation, right? And same thing I can do here, right? So with this exponent, I can add a full period, right? So I multiply by n and I divide by n, right? So again, and I take minus here with minus here. So it's equal to this expression, okay? So bottom line doing it, what now appears here is a summation that looks like this. Now, what is written here? It's just the Fourier transform of theta, right? So basically the eigenvalues are the Fourier transform of this vector theta. Okay? So the circular matrix looks like this. So it's phi diagonal matrix of the Fourier transform of theta phi star, right? And this gives this duality between the convolution in the spatial domain and the convolution in the frequency domain, right? So in the spatial domain, I can do the convolution by multiplying by a circulant matrix. In the frequency domain, I can take my signal, first compute its Fourier transform, then multiply by the diagonal matrix, which is formed as the Fourier transform of this vector theta, right? And then do element-wise product, and then compute the inverse Fourier transform, right? So often when people do signal filtering, they already design the filter here, right? So nobody computes the Fourier transform of theta. You already design its Fourier transform, right? Because when I design a filter, right, I, for example, want to amplify low frequencies or high frequencies, right, depending on what the filter tries to do. So I only compute the Fourier transform of the signal itself, of the vector x. Okay? Is it clear? Any questions? Have you seen Fourier transform before? Yeah, there is a question.
Why are we doing it in the frequency domain? Is it better?
So why are we doing it in the frequency domain? So first of all, it's, well, you can interpret it in as frequencies, right? So that's how we think of filters. So we can basically talk about low frequencies and high frequencies, right? So basically that's a convenient way of representing signals. In other cases, we don't have the spatial definition of convolution. So when you have a graph, for example, or a manifold, right? There is no clear notion of what is a convolution, right? But the Fourier transform can still be defined. So that's why it is very general construction, right? So once you do the Fourier transform, you forget about the underlying domain, you only work with Fourier coefficients. So this allows us to extend the notion of convolution to domains where you don't have a very easy way of defining convolutions.
But in the age of deep learning, nobody designs vector.
So in deep learning, you would be learning these coefficients. So you learn the filter, right? But again, in convolutional neural networks, typically you also take a window, right? So your filter is supported on some compact domain in the spatial domain, right? So you take something like 5 by 5 blocks. So it's actually inconvenient to work in the frequency domain. But in, for example, in one-dimensional signals, for example, when you have speech, it might be the other way around. It's more convenient when the support of the filter is large in the spatial domain, it will be usually small in the frequency domain. Right? We have the uncertainty principle, right? So the Heisenberg principle relates the support, right, or the variance of the filter in the spatial domain and the frequency domain, right? So if it's small in the spatial domain, it will be large in the frequency domain and vice versa. So if I need a large filter in space, right, or in time, it will be small in the frequency, and that's why it would be convenient to work with the frequency-based representation. Okay, questions? So repeat the question. Sorry, I didn't.
Maybe it's a question, but if we are doing convolution, I can run convolution network or something like that. So we are multiplying with the convolution network. So we are doing that in the spatial domain or?
So usually in convolutional neural networks that are applied to images, you do it in the spatial domain. Yeah, but again, so this is a general idea, right? So this relation always exists. What is more convenient? So for images, it is more convenient to do it in the spatial domain. For acoustic signals, for example, it could be the other way around. So usually for acoustic signals, actually filters are not done in the spatial domain; they're done in the frequency domain. Yeah, but it depends on the application, right? So. But again, we'll see why it is convenient to define the Fourier transform, because on a graph where you don't have an immediate notion of convolution, this thing still works, right? Okay? Good. So let's talk a little bit about geometric stability. So I think Theodora alluded to it in the very beginning, right? So, and we have, when we talk about about invariance, right? So what would be the simplest shift invariant, right? So I could just take the absolute value of the Fourier transform, right? So how does it work? Basically, shift in time, right, or in space becomes a complex phase in the Fourier domain, right? So it's just modulation by this complex sinusoid. So if I take the absolute value, I get rid of it, right? So I lose some information, but at least I got rid of the effect of the shift, right? So basically, I can, here is a candidate, right? So you wanted a nonlinear shift invariant, so take the modulus of the Fourier transform. Is it a good idea, right? So first of all, you can prove that it's an invariant, right? So shift becomes this in the Fourier domain, right? And when I take the absolute value, this complex exponent goes, right? So it's obviously an invariant. Is this invariant stable, right? So basically what I want to do is to be able to say that, okay, so under the action of the group, right, which is in our case is the shift, it is invariant, right? But if I don't have a perfect translation, if I have something that looks almost like a translation, but it's something more general, right? So basically when I'm sufficiently close to the group, right? How far will this invariant take me from the ideal case, right? So I want some sort of stability, right? And so this is an example, right? So the difference between a translation and a warping, right? I can basically consider a bigger group of general diffeomorphisms on my domain, right? And I can measure, for example, how far it is from a shift by using the Dirichlet energy, right? So we'll talk about Dirichlet energy later, right? But it's basically sum or integral over the squared norm of the gradient, right? And if it's perfect shift, then of course the gradient, right, of constant function is 0, and therefore the Dirichlet energy is 0. But if I have a general warp, then it will be non-zero. Okay. So that's basically an idea. If I have something that looks almost like a shift, but it also warps, will this absolute value of the Fourier transform still be a good invariant, right? So the answer is no. And here is an explicit construction of an example that shows that this is not stable. So I have this signal, right? So it looks like this. So it is a sinusoid, right? So this complex exponential with some frequency psi 0 multiplied by some window, right? So it's localized in time, right? So basically it decays, right, and becomes 0, and it's also localized in frequency, right? Because I modulate it with this frequency psi 0, right? So if I look at the Fourier transform, right? So how does the Fourier transform of a product of two signals look like? Looks like it's a convolution of their Fourier transforms, right? So convolution of so Fourier transform of a Gaussian is a Gaussian, right? And this sinusoid is a delta, right? So convolution of a Gaussian with the delta will be Gaussian located at this frequency psi 0, okay? With certain variance, right? So the variance depends here on the definition of this x, h, okay? So let's say that I now produce a warped version of this signal, right? So my transformation here is not exact shift. It looks something like this: 1 plus SU, right? Where S is very small, right? So it would have looked like a shift if it was not for this S, right? Okay. Now, what happens to the Fourier transform, right? So this is how the signal looks like, right? So it's almost a shifted version, right? But it's also slightly distorted. So how the Fourier transform looks like, right? So we have a new frequency now. So it's 1 plus S psi 0, right? And the width of this window. Did we lose the sound? Can you still hear me? Yep. I think there is some battery issue here. Or what is it? Can you hear me now? No. This microphone. Right, so basically in this example again, so the Fourier transform of this new warped signal looks like this, right? So it's now it's again this window that might have slightly different variance, right? But again, changed very little, but just by this factor S. right? And now it's centered around a different frequency. So the purpose of this construction, if I can choose S in such a way that these two things do not overlap, right? I can basically say that I have infinitesimally small modification of my signal, but very different Fourier transforms, right? So if I take the absolute value, you see that they almost do not overlap, right? So the difference between the modulus of this Fourier transform of the original signal and the warped one can be arbitrarily large, right? You see, so basically it's not stable anymore. So even though my initial modification of the original signal is very small, the modification of the output is arbitrarily large, right? So it's order of 1, right? And this is a problem, right? And we can see it here. So if I plot the spectrogram, right? So the joint plot of basically the short time Fourier transform. So here is the space and here is the frequency, right? So this is the original signal and this is the warp signal. You can see that what is mostly affected are the high frequencies, right? So they are mostly affected by this dilation. The low frequencies are stable. But if we remove the high frequencies, right? So if I just apply a low pass filter, I lose information, right? So it's like averaging the image, right? So it's not good. So the key challenge is how to stabilize the high frequencies without losing the information, right? So here comes the second part of the discussion that I wanted to skip because it would require to define wavelets, and I don't want to torture you with this more intricate harmonic analysis. This is what convolutional neural networks achieve by doing pooling. So basically, the mathematical analogy of pooling that is used in convolutional neural networks is called the scattering transform, and that's exactly this kind of pushing these unstable frequencies to a different scale in this decomposition and stabilizing them. So this is what convolutional neural networks do. There is a beautiful series of talks by Stéphane Mallat that studied it. So basically, that's, in my view, the best mathematical explanation telling why actually convolutional neural networks learn geometrically stable representations. Okay. So last thing I want to mention, I briefly alluded to it, right? So the way we look at the convolution and how it can be generalized to other groups, right? So again, the way to think of convolution, you can think of it as a sliding window, right? So I extract a patch of pixels from an image, multiplied by some weights, right, that are learnable in a convolutional neural network, and I move it to a different position, right? So in other words, convolution is matching of a shifted filter, right? So I can write it as inner product of a translated filter, right? So S here is the shift operator, right? And we can write it like this, right? So whether the filter is flipped or not, it depends on the definition of the convolution. And again, we can do it because there is one-to-one correspondence between the domain and the elements of the group, right? So for every element of the translation group, I can find a point on the domain to which I shift, right? This is not the general case, right? So the fact that the convolution produces output from omega to omega, right, or space of signals on omega to the space of signals on omega, this is rather an exception. So if I have a general group, right, not necessarily shift, even think of the same grid, you have a group of shifts and rotations, right? So it will not look like this anymore. So now we have a general group representation, right? So we need to act on it on our filter. And the output will now be defined for every element of the group. So the output will live in the space of signals on the group, right? It doesn't need to be necessarily the same structure of the grid, right? So again, if I have rotations, it will look like something like a sphere, right? So not anymore a grid, right? And you can define convolutions on these things as well. And there are generalizations of convolutional neural networks that can deal with things like signals defined on a sphere, okay? So it is, again, slightly more intricate, so it requires some extra machinery from group theory, and I would like to skip it. So this is what we typically teach in these courses at Oxford, but I will spare you these details. Okay? Any questions about grids and convolutions and Fourier transforms?
Sir, the convolution space is from the original space, signal space of sigma to the group space.
Yep.
In this case. So like any intuition into it, like why does it matter to convolution? Like it's not very clear.
So imagine that you have a signal that is defined on the sphere, right? And there, the natural transformations are rotations, right? So the sphere is a two-dimensional manifold, right? So the coordinates on the sphere are azimuth and elevation, right? So the rotation group is three-dimensional. So you can rotate up and down, left and right, and around yourself, right? So it's a three-dimensional manifold, right? So SO3 is, it is a manifold, right? So it's three-dimensional, it's a Lie group. So you see that even the dimensionality of the input and the output is different, right? So the next layer of convolution will need to go from the group to the group again, right? So it will basically, you will need to write this integral on the SO3, right? On the group of rotations. Again, there are ways, the right ways of doing it. There is also a Fourier transform for these kind of things. I just didn't want to go into these details.
So other types of convolutions like from SO3 are this popular or have this applications?
Yeah, so they have been used in. So you can extend, for example, standard convolutional neural networks to also account for rotations. Yeah. So there is a general recipe for building it. So with steerable filters, but it requires again a bit of heavy lifting from group theory. More questions? Yep.
Thank you for the lecture. My question was like how, sorry, maybe I didn't get the conceptual idea, but how exactly the convolution is connected with the Fourier transform, or the Fourier transform was just a way to show a history that it made us to go with the convolution idea.
So the Fourier transform is connected to convolution by being, so the Fourier bases are the eigenvectors of the convolution matrices. So all convolution matrices have the same eigenvectors, and these eigenvectors happen to be the Fourier bases.
All right, got it.
So the Fourier transform is this particular set of orthogonal vectors that diagonalize the convolution. Every convolution, right? Because all convolutions commute, therefore they're jointly diagonalizable, and they're diagonalized by the Fourier transform.
All right, yeah, thank you very much.
So there is another way of deriving it, right? So you can think of the Fourier transform as irreducible representation of this group. So there is this more general notion, and you can define it also for other groups. So, for example, in quantum mechanics, people deal with rotations. So spherical harmonics are the spherical version of the Fourier transform. So, and it can be more general. So in quantum mechanics, it's called the Wigner D matrices.
I think you and maybe a question, are there can be like, references applied for like maybe a little bit more deeper getting into this idea is possible?
Yeah, of course. So I have here at the end some references. Yeah, so even a blog post, but this one is the best way of deriving convolution from first principles, and this is the geometric stability of the CNNs, Bruno and Mela.
Thank you very much.
Good. So let's move on then, and we can talk now about